In recent videos in this series, we've been delving into some of the mathematics of quantum mechanics as regards the spin of an electron. We've got our Hilbert space for a single electron, our basis states of up and down, which we tended to put as the labels of the Hilbert space axes. We also have our three sigma matrices for the x, y and z directions, those operators that will allow measurements in a mathematical sense to be made on the spin states. So far, however, we've been looking only at a single particle spin system, exemplified by a single electron. This has a spin angular momentum s equal to h bar over 2, and it is known as a spin-a-half particle, a member of the fermion family. In the classical model, this rotating charged mass could be said to give rise to a magnetic moment. But as far as quantum mechanics is concerned, we have to say that it just has a magnetic moment mu, represented in the case of the negative electron by a vector in the opposite direction to its angular momentum. We discussed some of the experimental idiosyncrasies of such a particle, typified by the results of the Stern-Gerlach experiment, and then looked at the way physicists had developed a mathematical theory to account for what seems to us with our classical minds to be some of the strange behaviour of these particles. The part of the quantum theory that we explored was concerned only with the state of the electron's spin, and not with whether it might be moving in space or its kinetic energy or potential energy or whatever. In fact, as the Hilbert space showed, we worked with only two basic states that the particle could be in, which we called the basis states, and these were concerned with whether its spin was pointing up or down in the z direction of real space. The two basis states for the single electron were written as what are called ket vectors, up and down, which we wrote like this: U for up and D for down. The Z subscript of the label within each ket bracket is not really necessary, but was added simply to remind us that we mean up and down in the Z direction. We also realized that, strange as it may have seemed at first, we could use mixtures of these two states to write down state vectors for electrons with their spins in the positive and negative x and y directions. You should recall that this is because the mixing takes place in Hilbert space, where the angles between things, if I can use that language, the angles are different to those in real space. As has been said, we also had three operators called the sigma matrices, which allowed us mathematically to measure the component of the spin of the electron in various directions. These were called sigma x, sigma y and sigma z. We got a sense of the logic of all this by thinking of the up and down states as being column vectors in Hilbert space, and of the spin operators as being 2x2 matrices. As mentioned a moment ago, we also found that the right, left and in, out states could be written in terms of the up and down states, and that made it fairly easy to see that the application of these spin matrices on the spin states would, in certain circumstances, give a measurement of the spin as being +1 or -1. This was when the result gave the same state but multiplied by a real constant number, +1 or -1. After playing with the various matrices and column vectors, we were able to write the 6 relationships like this, which related to the measuring of the component of the spin direction. There were some circumstances, however, in which the application of a sigma matrix onto a state did not give a measurement, but rather changed the state in some way. Some of the important relationships that we ended up with in terms of these changes were considered to be those where the sigma matrices acted on the two basis states, up and down. We noted that the x and y sigma matrices flipped the up and down states, sometimes throwing in i's or minus i's, whereas the sigma z, of course, simply measured the up and down states. All this worked out reasonably sensibly, and we went on to assume that these three sigma matrices could somehow be combined into new ones, like vectors in real space, so that the spin components in any direction in space could be found, although we didn't go into the mathematical details of how to do that. As has been said, we imagine the basis states of up and down to exist in some imaginary two-dimensional space which we called Hilbert space, and we said that the two states lay on axes that were orthogonal to one another. The flat screen that you're looking at is meant to represent the imaginary two-dimensional Hilbert space, and the low up and down are 180 degrees apart in real space. The up and down states are shown to be 90 degrees apart in this depiction of Hilbert space. Each of the two states represented by these kets was normalized, or in simplistic terms, each one was of unit length. They were also, in a sense, at right angles to one another in the Hilbert space. Strictly speaking, therefore, the up and down states should really be represented by these small arrows of unit length, although, as mentioned earlier, in order to save clutter, we tended to label the axes with the two ket representations. We now come to the point, however, where we need to consider two electrons at the same time. And I suppose the first thing we need to do is to decide how we will label their individual state vectors. I'm going to call them electron A and electron B. And once again, I'm going to assume that we only need to consider spin up and spin down in the z direction for each of them. My suggestion for labeling them is to do it like this: up A and down A for electron A, and up B and down B for electron B. Yes, and I know it looks cumbersome with all the extra indices, and I may clean it up in a moment. Each electron state has its own superscript A or B, and at the moment all four of them have the unnecessary reminder that the U and D stand for up and down in the Z direction. When thinking about two electrons together, we are going to need, however, a new Hilbert space, and also we'll need a new set of basis vectors that can live in that space. We need to realize that the system we have up to this point is such that these two electrons, when considered separately, have their own Hilbert space as far as spin states are concerned. The plane of this Hilbert space of electron A is another world away from the plane of this Hilbert space for electron B. They are definitely not the same Hilbert space. We need to find a way of bringing them together into a new Hilbert space. It will of course necessarily be a four-dimensional space, and it should be obvious that however much we try to explain this, there is no way we can, for 4 dimensions, draw anything remotely similar to the flat plane representation of the Hilbert space of a single electron. It should be reasonable, however, to believe that if you bring two-dimensional spaces together, then unless some of the dimensions happen to coincide, which they don't, you're going to end up with 4 dimensions. Mathematically, the way of bringing the spaces together is to find what is called the tensor product of them. Now, we don't need to go into the mathematics of this, but maybe this picture will help. Here's a simple representation of the two-dimensional space for the electron A, showing up and down, drawn horizontally here on the screen. And here's a similar representation of the two-dimensional space for the electron B, drawn vertically on the screen. There's electron A with its two states up and down, and there's electron B with its two states up and down. Now, it should be obvious that there are 4 permutations of these in a kind of cross-tabulation, and I'm suggesting that each one of these 4 permutations should represent a basis vector for our new system. Effectively, each one of them is a dimension of the new system. This label will denote the state of the 2 electrons where A is up and B is up. This label will denote the state of the 2 electrons where A is up and B is down. This label will denote the state where A is down and B is up. And this label will denote the state where A is down and B is down. Again, it should be obvious that if each electron can only either be up or down when the component of the spin is measured in the z direction, then these 4 states are the only possible situations for 2 electrons considered together. We could, of course, have used arrows for these labels. Up arrows here, down, up arrows here, and so on. But I'm going to stick with U and D and the indices A and B, even though the first one of the two will always be A and the second one will always be B. I will therefore use this notation for the four basis states of the four-dimensional Hilbert space of the two electrons A and B considered together, where I've put the labels from the cross-tabulation inside the ket brackets for the new states. The four things are now to be thought of as ket vectors. You'll notice that I have at last taken out the unnecessary Z. In fact, even though it should be obvious that the first entry in each ket is for electron A and the second for electron B, I shall from now on colour electron A amber and electron B blue. Now don't worry if the amber looks a bit like red on your screen. It's supposed to be A for amber and B for blue, but at least the Z reminders have gone at last. As these are the four basis states that make up the four-dimensional Hilbert space for the two electrons, we will assume two things about them. First of all, each one of the four of them is normalized, and secondly, they are orthogonal to each other. Now, normalization is akin to the state vectors having unit length in Hilbert space, so that the inner product of each one with itself is 1. Up up with up up is 1. Up down with up down is 1, and so on. As to the second assumption, that the state vectors are orthogonal to one another, this implies that the inner product of one state with any other different state must be 0. I shouldn't use this phrase, but they are in a sense at right angles to one another, if I can say that about a Hilbert space, and a four-dimensional Hilbert space at that. The orthogonality condition is shown in these 6 combinations. There's up up, orthogonal to the other 3, giving a 0 inner product, and these show the other arrangements, which are also orthogonal. So we now have symbols, or kets, for our four basis states, which represent two electrons considered together. We could explore how these four kets could be combined to produce states describing two electrons with their spins in other directions like x and y, or somewhere in between, and we could write the general state as A times up up plus B times up down plus C times down up plus D times down down. In which case, different values of the complex numbers A, B, C and D will produce lots of different mixed states with each spin A and B pointing in different directions. However, we don't really need to explore anything like this general state or spin components in other directions, so we'll leave that. We will only need the mathematics to describe A and B each pointing up and down in the Z direction. We may well still need to combine some of these four states to produce the state for a pair of electrons, but there won't be any question of them pointing in directions other than up and down in the Z direction in anything that we'll be discussing. What we will do with these states will actually be quite simple. I should also say that at this stage I'm not concerned at the moment whether these two electrons, A and B, are entangled or not. They could be entirely independent of one another and totally unaware of one another's presence, or they could have interacted in some way with one another in the past, and their spins may have some relationship to one another. And this will be reflected in the combination of the basis states that will form the new state vector for the two electrons. The state may be a bit of one of these and a bit of another. Usually, in the situations we'll be considering, at least two of the constants A, B, C or D will be 0, and we will have at most 2 terms for our situations, but we'll get to that later. Before we do, we need to clarify exactly how the components of the spins will be measured for this state that will describe the two electrons together. When we had one electron, we had 3 sigma matrices, which were the operators used to measure the spin components in the x, y and z directions, sigma x, sigma y and sigma z. Sigma x will be used to measure the component of the spin in the x direction, And the only time that it gave a measurement of +1 or -1 was when it was applied to the right or left states, each of which was a mixture of the up and down basis states. Similarly, sigma y could be used to measure the component of the spin in the y direction, and that only gave a measurement when it was applied to the in and out states. Sigma z, of course, could be used to measure the component of the spin in the z direction, and that only gave a measurement when it was applied to the basis states, the up and down states. These were the obvious uses for the sigmas to measure the component of the spin in the direction that the spin was known to be along. Sigma x for a spin along the x direction, sigma y for a spin along the y direction, and so on. However, as was mentioned earlier, after we had studied the sigma matrices, an important conclusion that we reached related to what the three of them would do when applied to each of the two basis states of the system for one electron, the up and down states. The results were these, and I suggested that it was important to get the basic idea of these into your head. We've already just said that the sigma z acting on the up and down states simply makes a measurement of the component of the spin in that direction. It gives the same state after, but multiplied either by +1 or -1. And that number is taken as the measurement of the spin component in the z direction of that state. +1 in the positive z direction, -1 in the negative z direction. Sigma x or sigma y acting on the up and down states don't produce measurements. They change the state from up to down or from down to up, and on top of that sigma y throws in an I and maybe a minus sign as well. So that was all we needed to know about the three sigma matrices for a single electron. However, we're now studying two electrons together. And this means that we have four basis states for this two-electron system. And one or more of these will be part of what we will have for the new state vector describing the two electrons. Each electron, A and B, could surely have its spin component measured or its spin flipped, independent of what's happening to the other electron. This means we're going to need two sets of sigma matrices. One set that will act on the A electron for measuring it or doing things to it, and one set that will act only on the B electron for measuring it and doing things to it. You may recall that with our system for one electron, we got the sigma matrices by thinking about the state vectors as column vectors. We did this kind of thing. Sigma x acting on the up state of a single electron was understood mathematically to be from a 2 by 2 matrix for sigma x acting on the column vector for the up state, 1, 0, and it gave the answer 0, 1. It flipped the state to down. And rather than write out matrices each time like this, we found it easier to write this kind of thing simply as sigma x on the up state equals the down state. So I suppose here, now that we have four basis states for this two-electron system and a four-dimensional Hilbert space for them to live in, we could think in terms of each of them being a column vector with four numbers in it. Now we're not going to pursue this, but here's what such a system could look like. Here are the four possible column vectors for the four basis states. A 1 here would represent the electron A up and electron B up. Here, electron A is up and B is down. Here, A is down and B is up. And here, electron A is down and B is down. You can see that we've just used each of the four positions on the column vector, the four-dimensional column vector, to identify one of the four states, and we've used the number 1. The state would obviously be normalized, as one of the entries is 1 and all the others are 0. 1 squared plus 0 squared plus 0 squared is bound to be 1. On top of that, we could write down 6 4 by 4 matrices that could be used to measure the component of the spin of each of the electrons A and B in the x, y and z directions. We would need 6 because we'd need 3 for electron A and 3 for electron B. I won't write these all out, but here's an example of one of those possible matrices acting on a basis state. This particular one represents sigma x for electron A acting on the up-down state, the state where A is up and B is down. This has a 1 in the second position. As you might expect, sigma AX only affects the A electron, and it always flips up to down and down to up, so here it flips up to down. This is the down-down state, with a 1 in the bottom entry of the column vector. You could check this four-dimensional matrix multiplication for yourself, but I wouldn't bother. The reason being is that we don't actually need to go into all this trouble of thinking about four-dimensional column vectors and 4x4 spin matrices. We can treat things much more simply. The fact that the sigma AX has simply flipped the A electron from up to down and has done nothing to the B electron means that if we want to apply sigma AX to the up-down state, we can simply use this kind of shorthand. Here we're using our old 2x2 spin matrix for X acting on the state up-down, but thinking in terms of it only acting on the A electron. As usual, this sigma X simply flips the up to down, but of course only for the A electron, and it leaves the B electron unaltered. The B electron stays as a down in this example. We then get the right answer for the new state, down, down. We don't therefore need to get into four-dimensional vectors. All we really need is a second set of 2x2 sigma matrices, one that will only act on the B electron. I will call one set the sigma A's and the second set the sigma B's, and again I'll colour them. Those which act on electron A will be amber, and those for electron B will be blue. So rather than have to construct these as some kind of 4x4 matrices, we'll simply think in terms of sigma A's as acting on electron A and sigma B's as acting on electron B, and in that way we can continue to think of them as 2x2 matrices. This would mean that each set of the three sigmas would look identical if written in this simplistic matrix form, but they are clearly very different in the way they act. What I mean is, we'll assume that sigma AX as a matrix looks the same as sigma BX, and so on. But, and it's a very important but, when acting on a state in our four-dimensional Hilbert space, the A sigmas would only act on and do anything to the electron A, and the B sigmas would only act on and do anything to electron B. In that sense, we will not be delving into what any matrix multiplication of four-dimensional column vectors will look like. We don't need to. We know exactly what the various sigmas do to up and down. Here's our list from the single electron situation, which I hope you'll be getting used to by now. These will give us the rules, providing we remember to operate on electron A or electron B as appropriate. Just to reiterate, now that we know exactly what these sigmas do, we can dispense with the need to consider the column vectors and just use relationships like these. However, now we have to think in terms of the A sigmas only acting on the part of the state for electron A and the B sigmas acting on the B part. Some examples will, I hope, help to see how simple this idea is. Let's suppose that we had some state vector for the two electrons A and B such that electron A was down and electron B was up. And suppose we wanted to apply sigma X for the A electron to it. We could again easily work out that it would give the state up, up. The reasoning behind this is that sigma AX only acts on the A electron and the B electron is unaffected by it. In other words, sigma AX on the down A bit will flip it to the up state and give a multiplier of +1, the electron B being unaffected. So the final state is simply up, up in the Hilbert space. There is a multiplier of +1, but clearly we don't see it here. Another example where you would see something is, say, if sigma Z for the B electron, sigma BZ, acted on the up-down state, i.e. the state where electron A was up and electron B was down. Sigma Bz only acts on the B electron. This sigma Z actually measures the B spin in this case. It doesn't flip it but leaves it down and multiplies the state by -1. Consequently, we end up with -1 times the same up-down state. Even though it was the B electron that caused the multiplier -1 to be included, that multiplier goes outside the ket of the new state, as of course it must. This simple way of working means that we now have all the mathematics we're likely to need in order to deal with two electrons at the same time. We have the four-dimensional Hilbert space. We have the ket representation of the four basis vectors in that space, and our symbols for them contain information on each of the two electrons A and B, information about their spins. We have the sigma operators, the measurers, if you like, of the spin component in various directions, and we know exactly what they do to each of the four basis states because we know what they do to their respective electrons A and B. We shouldn't really need to write out a long list of what the sigma A's and sigma B's do to the four basis states. If we did, it would contain 24 equations in all, 3 sigmas times 2 electrons times 4 states. If you want to see them all, then here they are, but it would be pointless to go through each one of them. I'll mention the groups. There are the 3 sigma A's, X, Y, and Z, each acting on the 4 states, making 12 equations altogether. And there are the 3 sigma B's acting on the 4 states, another 12 of them, 24 altogether. Looking at this one as an illustration, we have a state where both electrons A and B have their spins down, the down-down state. And we want to measure mathematically the spin component of the A electron in the X direction, and to do this we apply sigma AX to the whole state. The sigma AX acts only on the A electron, which is down, and from our list of what the sigma matrices do, a sigma X will flip down to up and I suppose multiply by +1. The A electron in this state therefore goes from down to up, and the whole state is multiplied by 1. And this gives the final result as up-down. Now you can check others out for yourself if you wish by pausing this video. As I say, we don't really need this long list. All we really need to be aware of is the original sigma actions on the states for a single electron. Sigma X and sigma Y flip the spin and maybe throw in an I and a -1 in the case of sigma Y, and sigma Z leaves the state as it was but multiplies by either +1 or -1. And having this list in mind, we should be able to deal with any situation, as long as we remember whether the sigma we're using is for A or B, and whether it is for X, Y or Z. I said I didn't need to go through any of these, but here's one more example of one of the 24, just in case anyone is uncertain. Consider this situation. Imagine in our later deliberations we need to apply sigma By onto the state down up. That's A down and B up. In other words, we have a state of 2 electrons. A has its spin down in the Z direction and B has its spin up in the Z direction, and we want to try to measure the component of the spin of electron B in the Y direction. It won't actually make a measurement, of course, it will flip things, but let's do it anyway. Being a B sigma, it is only going to affect electron B. The colouring should help here. The sigma Y is going to have to act on the up state, because B here is in the up state. From our simplified list for a single electron, the rule for sigma Y acting on an up state is that it flips this up state to a down state and also multiplies the state by I. This means that when sigma By acts on the A down, B up, it acts only on the B electron, which, being in the up state, gets flipped to down. However, the action also multiplies the whole state by I. I'll stress again that the I doesn't go inside the ket in front of the B electron part of it, even though it was the flipping of the B electron that was responsible for the multiplication by I. It would be silly to put any multiplier inside the ket. We said very early on that what goes inside the ket is just a label. It's the whole state itself that gets multiplied by any factors, in this case by I. As we saw, there are 24 such equations for all the combinations of sigmas, electrons and basis states. 3 sigmas times 2 electrons times 4 states. And this whole business may all seem rather complicated and abstract at this stage. And in some ways, of course, it is abstract. But I hope you will begin to see later how that it is a fairly simple use of the mathematics, but also you will realize that it gives some insight into an explanation of entanglement once we get to it. All you need to be confident about at this stage, however, is that number 1, you accept the various actions of the sigma matrices when they act on an up or a down state. If you're not confident, go back and look at the way the sigma matrices affected the column vectors when we discussed them early on for a single electron. These equations are just the shorthand form of those matrix multiplications for a single electron. Secondly, we need to be confident about having 2 sets of these sigma matrices, one set for electron A and one set for electron B. Thirdly, we need to feel comfortable that for 2 electrons, entangled or not, we now have 4 basis states in a 4-dimensional Hilbert space. And fourthly, we need to understand that the new sigma matrices can act on these 4 states, but the A matrices can only affect the A part of the state, and the B matrices can only affect the B part of the state. Any multipliers, of course, that are created go outside the whole ket for the state. As I said earlier, don't worry if all this seems rather complicated. The way in which it will be used is really very straightforward, so long as you are reasonably comfortable with these 4 requirements. Again, all this applies to any pair of electrons, or rather to any pair of these theoretical electrons that we're considering, where for simplicity we've suspended electrostatic repulsion and also ignored 1 or 2 other physics ideas such as the concept of identical particles. We want to think simply about the entanglement of 2 spins. But in order to get to entanglement, we wish now to consider the various ways in which we can have a pair of these spins, or as we'll continue to say, these electrons. What are the different ways of having 2 electrons, A and B, as far as their spins are concerned? And I'm going to suggest 3 ways in which the 2 spins can be considered. Number 1, the spins A and B can be independent of one another. Number 2, the spins A and B can be in the same direction as one another and add together. And number 3, the spins A and B can be in opposite directions to one another and balance out. We'll think about these 3 situations in a little detail in what follows, but our main concern will be with the last one of them, when the spins balance out. That will be the situation we will think about when we get into entanglement in earnest. If you want to skip the first 2 of these, which take about 25 minutes or so to the end of this video, then you can simply move on to the next video, number 9, which will start with the 3rd of these possibilities and launch into entanglement proper. Let's take the first example briefly. Independent electrons, the product state. Let's suppose that electron A is entirely independent of electron B. They have each been prepared separately from one another, and each spin is pointing in some direction in space which is not known by the other electron, if I can use that kind of anthropic terminology. We recall that single individual electrons can be said to have a definite direction for their spin in real space, even if that direction is not known by the experimenter. We argued this from the fact that it is impossible to find a general state for an electron, a mixture of up and down basis states, such that the average value of sigma x, sigma y and sigma z are all equal to 0 at the same time. we concluded that there must be a direction in space where, if you measure the components of the spin in that direction, you'll get an answer of +1 100% of the time. So I'm assuming that each of these separate electrons, A and B, have definite spin directions in space, but they are unknown to us and not related to one another in any way. They're not entangled or related in any way. We could write the general state for the electron A, assuming it's normalized, like this. As an individual electron, electron A is a mixture of the up and down basis states of its two-dimensional Hilbert space. The coefficients AU and AD can be complex and will determine the direction of the electron in real space. For example, and this should take you back to an earlier video, if AU is 0.924, which is cos 45/2, and AD is 0.383, which is sine 45/2, then the spin of the electron in this state A will point at 45 degrees to the z-axis in the xz plane. On the other hand, if AU and AD were each equal to 1/√2, or 0.707, then this would be the state for an electron pointing in the positive x direction to the right. However, whatever the values of AU and AD for this general state for the electron A, normalization requires that AU squared plus AD squared should be equal to 1, or strictly speaking, AU star plus AD star must equal 1. Now we could similarly write the general normalized state for electron B as this. Again, it is a mixture of the up and down basis states of its own particular two-dimensional Hilbert space, with coefficients BU and BD, which again must satisfy the normalization condition of BU star plus BD star is equal to 1. The question now is, can we write some kind of combined state for these two independent electrons? In other words, can we put everything together into one state using our new four-dimensional Hilbert space and yet still have the electrons behaving independently of one another? Well, the answer is yes. And the way to do this is to multiply those two states together. This kind of multiplication is known as the tensor product, and it will produce the combined state of the two electrons in terms of our new four-dimensional Hilbert space. You'll see what I mean in a minute. It's quite simple. Here is what we call the product state, shown as the straightforward multiplication of the two states, each in their own Hilbert space. There's the general state of the A electron with its coefficients multiplying the up and down states in its space, and there's the general state of the B electron with its coefficients multiplying the up and down states of its space. Now if we multiply out these two brackets, we get that the product state contains 4 terms. However, if you remember how we formed our new four-dimensional basis of states from the cross-tabulation of the other two, it should be obvious that these products of the two old basis states are the new basis states of our four-dimensional Hilbert space. This means we can rewrite them so that this product state can be written like this. As you might expect, this state is automatically normalized. And this is a consequence of the fact that the two states that made up this product state were themselves normalized. You could check this by playing around with the A's and B's. It's very easy. The product state with these coefficients clearly has something very special about it. There is something distinctive about these 4 coefficients in as much as they make this state to be that of completely independent electrons. If later on we use the 4 basis states to write down a 2-particle state which could not be formed from the product of 2 general states, in other words, a state where the coefficients don't have these special values and relationships where they relate to the original normalized A's and B's, then that state will be said to have some degree of entanglement. And we'll come across such entangled states later when we consider other mixtures of the basis states. Anyway, we'll say no more about the product state because it's of less interest to us at this stage. Such a state describes a situation where the electrons are independent of one another. Any measurements made on the product state using the various sigmas or whatever will be such that measurements on A will give us no information about B, and vice versa. The electrons are entirely independent of each other. So that's the first of the three situations that I wanted at least to mention concerning our new four-dimensional Hilbert space of states, namely the situation when the two electrons are entirely independent of one another. Now let's look at the second situation I wanted to focus on, that where the spins of the two electrons combine in such a way that they reinforce one another, they add up. So consider the situation where we have two electrons, A and B, but they are related in the sense that their spin angular momenta, SA and SB, are in the same direction as one another. Don't ask me how they could be stuck in this kind of situation, and remember again that they are hypothetical electrons. We're ignoring their electrostatic repulsion and the fact that they're identical particles. They're just two spins as far as we're concerned, and we want to use our basis states to describe them. Just accept that we have two hypothetical spin-a-half particles with their spins in the same direction. And I'll continue, of course, to call them simply electrons. We assume, therefore, that the two angular momenta h bar over 2 add up to one full h bar. We could write the total spin angular momentum S as the sum of the separate angular momenta of the two electrons, so that S is equal to h bar over 2 plus h bar over 2, which is equal to h bar. To go back to a single electron for the moment, you should recall that when we were dealing with a single electron, it had a spin angular momentum of h bar over 2. Furthermore, we realized from the Stern-Gerlach experiment that there could only be two results for a measurement of the components of that spin in a particular direction, namely plus h bar over 2 and minus h bar over 2. And we illustrated the idea with this diagram. It depicts the spin angular momentum in blue of a single electron pointing at an angle of theta degrees to the z direction. And we said that if we measure the component of the spin in the z direction, we either get plus h bar over 2 or minus h bar over 2. And the light blue arrows indicate the possible values of the z component of the spin for this angle theta. In this particular case, there is more chance of getting plus h bar over 2 than minus h bar over 2 because of the small angle of theta, and this is illustrated by the thickness of the two light blue arrows. There is no chance here that the measurement of the spin in the z direction would give 0. And this is because the angular momentum is h bar over 2, and quantum mechanics requires that only the two values are allowed, plus h bar over 2 and minus h bar over 2. Often, when dealing with a single electron, we work with ones rather than halves, and we talked about spin up being 1 and spin down being minus 1, and so the same kind of diagram for a spin-a-half particle like the electron could be drawn like this. Now don't be confused by the ones here. This was simply the other way in which we preferred to work. You'll notice I've drawn the spin in red. It's not the angular momentum, which would be blue, and it could be the magnetic moment, which we're saying is taken as plus 1 for up and minus 1 for down. It's just that we've doubled everything. Now all that was for a single electron. However, we are now considering two electrons which this time are constrained in some way to have their spins in the same direction. When that happens, of course, we will have a total spin angular momentum of one full h bar. And if you recall from our previous discussions, this means that there can now be three results for any measurement of the component of the spin in a chosen direction: plus h bar, 0, and minus h bar. We could illustrate this situation with this diagram. Again, we're showing an angular momentum in blue at theta degrees to the z direction, but this time it has a value of 1 full h-bar. Quantum mechanics tells us this time that if we measure the component of the spin in the z direction, we may get one of three answers: h-bar, 0, or minus h-bar. The light blue arrows and the dot are meant to represent these three possible values of the z component. Notice that there is now a possibility of getting an answer 0, even for the spin pointing, as we see it here, at some acute angle to the z-axis. The blue dot is meant to indicate a value of 0 for the component of the spin in the z direction. And you'll notice from the thicknesses of the lines I've drawn that the probability of getting minus h-bar is much less than that for the other two values, hopefully by now, for obvious reasons. Once again, however, we may prefer, in fact we do prefer, to think in terms of ones rather than halves for each electrons, in which case we would be saying that the sum of the spins is 2. And the same kind of diagram for two electrons with spins in the same direction would then look like this. Make sure you're comfortable with this and you don't get confused with it being 2 h-bar. It's not. It's 1 h-bar of spin angular momentum altogether. It's just that we prefer to work out the mathematics of quantum mechanics by talking about a single electron as having a spin of 1 rather than working with halves. Everything gets doubled and we don't include the symbol h-bar. Again, you'll notice I'm showing it in red just to emphasize the distinction for this way of looking at things. Also, given that there is nothing special about the z direction, you are, I'm sure, aware that when the component of this total spin 2 is measured in any direction, not just the z direction, there will be these three possible answers: 2, 0, and minus 2. The only exception to having multiple possible answers is if you just happen to measure the component in the direction in which the total spin is pointing, or in the opposite direction, or also here at right angles to them. The right angles measurement comes from the fact that the mathematics is different to what we had for spin a half, and we might see a little bit of that in a minute, but here's the descriptive bit, which should make reasonable sense from what we've already done. Consider these four scenarios. Consider a situation where the spin-2 combination is definitely pointing in the positive z direction. This means that if you measure the component of the spin in the z direction, you will definitely get the answer plus 2. The probability of getting the answers 0 or minus 2 for the component of the spin in the z direction is 0. So I've not put in any red dot or negative pointing arrow on the right. You would only definitely get minus 2 as an answer if you tried to measure the component of the spin in the negative z direction. Secondly, now consider the case where the spin-2 combination, the two electrons together, is definitely pointing at right angles to the z direction. With our usual axis, this would be in the negative x direction. This means that if you measure the component of the spin in the z direction, you will definitely get the answer 0, hence the red dot. You have 0 probability of getting the answers plus 2 or minus 2 in this measurement. We've not had that kind of situation before, but it would come out of the mathematics of the triplet state if we spent more time on it. Thirdly, and this should all be obvious by now, consider the case where the spin-2 combination is definitely pointing in the negative z direction. This means that if you measure the component of the spin in the z direction, you will definitely get the answer minus 2. You have 0 probability of getting the other two answers. And fourthly, I suppose we could go back to our more general situation where the spin-2 combination is pointing at some angle theta to the z-axis. In this case, measuring the component of the spin in the z direction could result in any one of three answers: plus 2, 0, or minus 2. You could get any one of the three answers, and although we won't explore it, the mathematics of quantum mechanics can provide the probabilities for each of them if theta is known. Similarly, if we measure the component of the spin in this direction, we could still get any one of the three answers, +2, 0 or -2. All three answers would have probabilities which would depend on the angle between the spin and the direction of the measuring device. Measuring like this, of course, would guarantee a measurement of +2 and this -2. Making this measurement would guarantee the answer 0, assuming I position the measuring device exactly at 90 degrees to the spin direction. Don't forget, it's for the single electron that an answer of 0 is impossible. Here, with two electrons whose spins add up in this way, the answer 0 is one of the three possibilities, and it occurs with certainty when you measure the component of the total spin at right angles to the actual direction of that spin. So, all that discussion was really just a reminder of what we're dealing with when we have a spin 2 system, or strictly a total angular momentum of 1 h-bar. With this whole situation, we can talk in terms of there being three states that the combined pair of electrons can be in, and for obvious reasons we call these the triplet states. What we now want to do is to think just a little bit about how the state of this spin 2 object 1 h-bar could be represented by our four basis vectors, which we understand to apply to any two electrons A and B, even when they're combined like this. Let's take the general situation again, where the total spin is pointing in a direction at some angle theta to the z direction. In a way, this is the general state. And from what we did with states for a single electron, it should seem reasonable that we can write this general spin 2 or 1 h-bar state in mathematical form like this. It's a kind of weighted mixture of the four basis states of the Hilbert space for the two electrons. The weights, or coefficients A, B, C and D, can, as usual, be complex numbers. Now we're not going to attempt to work out what these coefficients are for the state where the total spin is at theta degrees to the z direction. We'll just write it in like this, the sum of the four things. That yellow box is a representation of the state of these two electrons, which are constrained to have their spins adding up in this way, and with their total spin pointing in this direction at theta degrees to the z direction. Perhaps I'll show the four parts on top of one another so I can identify it better with this general state at theta. That's one way to write down the state for this pair of electrons with total spin pointing at theta degrees to the z-axis. It's a bit of everything. Of course, once the component of that total spin is measured in some other direction, then the state will collapse to something much simpler. For example, if we measure the component of the spin in the z direction, which is the whole point of this diagram, and we get the answer +2, surely it's obvious that the state then collapses to this. So we can write this here. The spin component of the whole thing in the z direction is now definitely 2, which means that both individual electron spins must be said to be pointing upwards in the z direction. The state is now, after this measurement, up, up. On the other hand, if we measure the component of the spin in the z direction as -2, then the state must collapse to this, and we can put this in. But what if the measurement of the z component of this total spin turned out to be 0? How can we represent this z direction measurement of 0 in terms of the basis states? This middle value in the triplet state means that even though the two spins are combining to a total value of 2, the spin component in the z direction will get measured as 0. It's as though, by classical thinking, the actual spin is being considered to be pointing in a direction at right angles to the z direction, so that when you measure the z component of it, you get 0. Now, from what little experience we've had of quantum mechanics, this seems to imply equal amounts of up and down in Hilbert space, if I can use that kind of loose language. Well, Here is what quantum mechanics says should be the shorthand for that situation. It's a normalized mixture of the basis states up-down and down-up, and it's important to note the plus sign between them. Hopefully you'll see why later. Conceptually, however, it may be difficult to grasp how this strange combination of up-down and down-up basis states in Hilbert space can in any way help to explain the measurement of zero spin in the z direction of real space, when we've been told that both spins are in the same direction as one another. But quantum mechanics is strange, and so for the moment, just accept it. These triplet states of up-up, down-down, and the combination of up-down and down-up do exhibit a degree of entanglement. But it's not this entanglement that we're going to explore in more detail. We could delve into these triplet states a bit more and ask what the various spin operators do to them, what measurements might be made, and also what the expectation values or average values of the various spin operators are in different directions. All of that would be quite informative, but for now I would rather get on to the third of the situations for the spins of two electrons, which will relate more easily to entanglement as I'd like to approach it. Let me remind you of the immediate context. In thinking about two electrons together, we've already discussed situations where, when the two electrons are completely independent of one another, it could be described by what we called the product state. However, there wasn't much we needed to say about this. The way the state vector was written looked a little unusual, but it was clearly showing that the two electrons were independent of one another. Nothing new really. Secondly, we've just briefly looked at the situation where the spins of the two electrons are in the same direction, or they combine to give a spin of 2, which is 1 h-bar. This gave rise to what is called a triplet state, about which much could be discussed, but we're not going to go there. Thirdly, and this will be looked at in the next video, there is the situation where the spins of the two electrons are in opposite directions to one another. If you like, the spins balance out. As we think about this in the next video, it will take us into some of the detail of quantum entanglement, and will finally enable us to appreciate something of the magic or mystery of quantum entanglement.